Hi everyone, welcome to our last video for week 5, where we're performing a hypothesis test for 2 proportions. Like the test for a single proportion or confidence intervals for a proportion, we are using the standard normal curve. So this is going to be a z-test because we're using the standard normal distribution as an approximation for something that is binomial in nature. So if we're looking at the traditional method, just like all other z-tests, we are looking up our value in table E or using inverse norm / inverse normal. If you're calculating the test value by hand, we have a similar formula to the test values for the other tests for 2 parameters. And we're going to do something similar. We know that we are by default assuming that those population parameters are equal. That's our null statement. And so this second part of the numerator is going to be 0. So that test value becomes the difference in the sample proportions divided by that square root. In that square root, you will notice 2 new values, PC and QC. PC is a pooled value. It is the sum of the x's divided by the sum of the n's. And QC is the complement, 1 minus PC. So P prime 1 is x1 over n1, P prime 2 is x2 over n2, and PC is the sum of the x's over the sum of the n. I don't know about you, but I'm lazy. So my instinct is use the calculator functions, and they are going to be the same calculator function that we're using for the p-value method. For the TI-84, you're going to go to the stat test menu and pull up option 6, 2 props z-test. Or in GeoGebra, the function call is the proportion to test. TI-84 is going to prompt you for what it needs. GeoGebra, you need the sample 1 proportion and sample 1 size, and then the same information for sample 2. Sample 2 proportion, sample 2 size, and then the tail determined by your alternative statement. Let's go ahead and do a couple examples. Starting with example 1, it says 2 types of medication for hives are being tested to determine if there is a difference in proportions of adult patient reaction. 20 out of a random sample of 200 adults given medication A still had hives 30 minutes after taking the medication. 12 out of another random sample of 200 given medication B still had hives 30 minutes after taking the medication. Test at a 1% level of significance. So let's go ahead and pick through that problem. Again, you'll notice there's not a table. So they gave us all the information in the word problem. And the very first thing it says is 2 types of medication are being tested to determine if there is a difference in proportions. So that tells me 2 important things. It's a test about proportions. So I know automatically it's a z-test. I also know it's 2 types of medication. So this is a test for 2 proportions. And they use the keyword difference. So when I run my hypothesis test, my alternative is going to be a not equal to. Then let's go ahead and color code the rest. So 20 out of a random 200 still had hives after 30 minutes. So that's X1 and N1. And then the next sentence says 12 out of 200 still had hives 30 minutes after taking the medication. So X2, N2. And then the very last piece of information they give us is tests at a 1% level of significance. Alpha equals 0.0. So first I'm going to organize my information. I'm given X1, whoops, not X1. I'm given X's and N's, and I'm given medication 1 and medication 2. I'm going to leave a little bit of extra room here. So column 1, we color coded in red, so that's 20 out of 200. Medication 2, we color coded in light green, so 12 out of 200. And then I've written this last row here for the P primes, 20 out of 200 and 12 out of 200. You don't have to write that, but if you are doing GeoGebra, it's going to ask you for P prime and N instead of X and N. So these two are for the TI-84, and these two are for GeoGebra. So which two pieces of information you need is going to depend on which technology you're using. I'm going to quickly jot down that alpha so I can clear off our scribbles on the other side of the screen. And then I know that I'm doing a z-test, for two proportions. So let's go ahead and jump into our p-value method. So I'm going to set up my structure, so I know what the structure looks like regardless of the type of test. Hypotheses and claim, calculate our p-value, make our comparison. So how does that p-value compare to our alpha? And then we're going to make a decision. And then step 4, we're going to summarize our results in Ascending. So for our hypotheses, we're dealing with two proportions, P1 and P2. We noted that keyword difference, so we know the alternative is not equal to, and that's the claim. And then our null is equal to by default. For step 2, I'm going to use the TI-84 for this first example. So let me pull my calculator over so we can see it. I'm in the stats test menu, and you can see option 6, 2 prop z-test. And I'm going to jot this information down so I can show my work. So 2 prop z-test, and then let's write down what it's asking for. So it's asking for x1, which is 20, and n1, which is 200. X2 is 12, N2 is 200, and our alternative is a not equal to. So you'll notice these tests for proportions tend to ask for less information because the calculator can calculate anything else it needs based on those X and N values. So it asks for less information, tends to go quicker. I'm going to type that in the calculator really quick. And then we hit calculate and we get a p-value. That's that third value down of 0.1404. 0.1404 is more than 10 times that alpha value. So p-value is greater than alpha. That means we're not going to reject. Do not reject the null. So what we're saying is the two proportions for medication 1 and medication 2 are not different enough that I am comfortable rejecting that null statement that they are equal. So we're going to summarize our results. So looking at our decision in step 3, do not reject, there is not enough evidence. And then we look at our alternative in step 1. It's The alternative is our claim. So support, there's not enough evidence to support the claim that. And then we go back to the word problem and look for what that claim is. And it says it's being tested to determine if there is a claim that there is a difference in proportions of adult patient reactions to med A and med 1 and med 2. Scoochie that up so it's on the screen. So there's not enough evidence to support the claim that there is a difference in proportions of adult patient reactions to med 1 and med 2. We can see from our data that for med 2, fewer adults out of that sample of 200 had hives after 30 minutes than med 1. So looking just at those two samples, we would assume that med 2 is probably more effective, but those proportions, 20 out of 200 and 12 out of 200, are not different enough that at the 1% level of significance, I am comfortable stating that there is a difference. So yes, we see a difference in the samples, but that difference in the samples is not big enough for me to feel comfortable extending that to the population. Okay, let's go ahead and try another one. Example 2, in a nursing home study, researchers found that 12 out of 34 randomly selected small nursing homes had a resident vaccination rate of less than 80%, while 17 out of 24 randomly selected large nursing homes had a vaccination rate of less than 80%. At alpha equals 0.05, test the claim that there is no difference in the proportions of the small and large nursing homes with a resident vaccination rate of less than 80%. So a lot of information thrown at us. Again, they weren't nice enough to give us a table. I'm going to focus on that very last sentence first, usually what we're being asked to do. It says test the claim. Know that it is a hypothesis test. And then the claim says that there is no difference in the proportions of blah, blah, blah. So this is a test of two proportions. No difference in proportions, plural. So we know we're doing a z-test. We know it's a test for two proportions. We also can see that we're testing it at a 5% level of significance. And then we're going to go pick information out of the problem. And there's some extra information here. If you continue reading that last sentence, it says test the claim that there is no difference in the proportions of small and large nursing homes. That's the end of our claim. And then what we're defining as a success is a resident vaccination rate of less than 80%. So that 80% is not a proportion. It's part of the definition of a success. So a resident vaccination rate of less than 80%, that's what we're calling a success for this particular study. That's what we were counting when we were counting how many people out of a larger sample met a requirement. So when we're reading through this word problem, picking off information that's relevant, we're ignoring the 80% because that's part of the definition of a success and not a relevant proportion. Going back to the beginning, in a nursing home study, researchers found that 12 out of 34 had that requirement for a success. So that's X1, N1, while 17 out of 24 had a vaccination rate of less than 80. So X2, N2. I'm going to go back and color code. Our sample 1 is the small nursing homes, and our sample 2 is the large nursing. So let's go ahead and summarize that information in a table. So we know we're given X and N. We know we're probably going to want P prime if we're using GeoGebra. And then we're dealing with small nursing homes, which are sample 1, and large nursing homes, which we're calling sample 2. Sorry that my pen tablet is a little squeaky. If you can hear that on the mic, I don't. Yeah, that's the pen tablet. So small is color-coded red, so 12 out of 34. We would write, oops, not, yeah, no, 12 out of 34 for our P prime if we're using GeoGebra. And then the large is color-coded in green, 17 out of 24. So 17 over 24 for our P prime. Our alpha is 0.05. And then this is a Z test for 2 proportions. I would encourage you to pause the video here and see if you can do that 4-step p-value method. I'm going to go ahead and work through it now. I'm going to set up my 4-step method really quick. Whoops. So I know I'm doing hypotheses. I'm finding my p-value. I'm comparing that p-value to the alpha of 0.05, and then I'm writing my conclusion. Back to step 1, a claim about proportions, P1, P2, P1, P2. If we go back to what we underlined in our word problem, test the claim that there is no difference. No difference means equal to. So the claim is actually the null. And our alternative is then the opposite of equal to, which is not equal to. For step 2, I'm going to go ahead and use GeoGebra. Since I did the TI-84 on the last one, GeoGebra, we're using Z proportion to test. I could spell to test, and it asks for 5 things. So it asks for p hat 1, which is 12 out of 34. And then it asks for N1, which is 34. And then the same for sample 2, 17 out of 24 and 24. And then the tail, which for us is going to be not equal to. So I'm going to go ahead and clear out all of the scribbles over here so we can see our GeoGebra window clearly. Let's go ahead and pull that up. So in our input box, we're going to type Z proportion. You can see it starts popping up with options here. 12 divided by 34, 34, and then 17 divided by 24. Oops. Not equal to. As soon as I press that, it pops up my p-value and our critical value. So our p-value is 0.0077, which is definitely smaller than 0.05. So we meet that requirement to reject the null. Our p-value is less than or equal to our alpha. So we're going to reject H0. And then our last step is to write that summary. I'm going to construct the sentence frame really quick. So based on step 3, we're rejecting, so there is enough evidence. And then going back to step 1, it's the null that's the claim. So we're talking about rejection. There is enough evidence to reject the claim that, And then we summarize that claim. There is no difference in the proportions. I'm going to stop typing because it's not going to fit on my frame, but I'm copying the information from that last sentence. So there is no difference in the proportions of small and large nursing homes with a resident vaccination rate of less than 80%. Okay, so I'm going to pop up example 3. Again, I'd encourage you to go ahead and try that on your own. And then I will pop back in just a second with the solution. Okay, for this third example, so the study found that in a random sample of 50 burglaries, 16% of the criminals were arrested. In a random sample of 50 car thefts, 12% of the criminals were arrested. At alpha equals 0.1, can it be concluded that the percentages of people who committed burglaries and were arrested was greater than the percentage of people who committed car thefts and were arrested? You can see I went through color-coded. Sample 1 is the burglaries. Sample 2 is the car thefts. I know my alpha is 0.1, and I'm very clearly performing a hypothesis test because it's asking me, can it be concluded? So we're testing a claim, and it uses the key phrase greater than. Burglaries are greater than car thefts. So sample 1 is greater than sample 2. You can see that becomes our alternative hypothesis. P1 greater than P2, when that's labeled as our claim. Our null is the equality. Because we were given P prime, I went with GeoGebra, which takes P prime versus TI-84, which will require X and N. So Z proportion 2 tests, and then sample 1 proportion, sample 1 size, sample 2 proportion, sample 2 size, and the tail in this case was greater than. And that gave me a p-value of 0.2822. For step 3, when we compare that p-value to 0.1, the p-value is greater, it's more than double. So we do not reject the null. In building our conclusion, we did not reject, so there's not enough evidence. And our claim was the alternative. So to support the claim that, and then you fill in information for the claim from the work. Okay, hopefully there have been enough examples that you're starting to feel fairly comfortable with that 4-step p-value method. Again, if you have questions, feel free to email me at any time or drop by office hours on Tuesday, Thursday, or Saturday. I hope you have a great rest of your week, and I'll see you in Canvas in the forums.